Hi, my name is Alexander Jones, and in this presentation I will be covering how to understand skeletal formula in organic chemistry. So this skill is often taught and utilized very early on in organic chemistry, as it becomes an easier way of drawing large organic molecules. So I'm going to start by teaching how structures are either similar or different as seen in the image here. And I will then teach how the octet rule or rule of 8 applies to this. And by this time we should be able to count the number of carbon atoms present in any molecule, as well as the number of hydrogens, number of oxygens, number of nitrogens, and so on. I'll also briefly discuss the differences between alkanes, alkenes, and alkynes as they relate to the structure of a molecule. And by the end of the video we should have a good understanding of how to interpret the chemical structure of any molecule as they appear, regardless of the formula that they're currently in. So I'm hoping this works, as I had to record my example and then speed it up so I could get the audio filled in time. So to begin, you really don't need to understand what the name of the molecule you're looking at is. You just need to understand that carbon is the backbone of any organic molecule, and as a result can form covalent bonds together. So now look at the molecule. As we see, there's 4 carbons, and we start by numbering the 4 carbons. Next, we'll redraw the molecule, numbering the 4 carbons again. However, instead of putting carbons in the actual molecule, we will replace the carbons with these intersections, as you see here. I've numbered these intersections to show you what stands for the actual carbon. Now, off of each carbon, I'm drawing the hydrogens as they appear on the original molecule. So as you can see, there's 3 hydrogens on carbon 1, so I add 3. There's 2 hydrogens on carbon 2, so I add 2, and so on. Finally, in step 3, I'm going to redraw this molecule without having the hydrogens present, and just having the simplified skeletal formula of the carbons. As you can see, the carbons are here, and we still have the exact same molecular formula. That does not change. So in the example seen before, carbon has 4 atoms bonded to it, these either being other carbons or hydrogens. So the trick to understanding this is understanding the octet rule, or rule of 8. This rule reflects the observation that main group elements tend to bond such that each atom has 8 electrons in its valence shell, giving it stable electron configuration, similar to a noble gas. So look at this example. Oxygen has 6 electrons in its valence shell ordinarily. All of the dots around the oxygen and carbon here are meant to represent electrons. Each oxygen, as seen here in red, have 6 of their own electrons in their valence shell, while carbon only has 4. We can draw upon these numbers from which group each of these elements resides here on the periodic table, oxygen being 6 and carbon being 4. Thus, when these 2 atoms of oxygen and carbon share in covalent bond, they can see that now, since the carbon is sharing its electrons with the oxygens, and the oxygens are vice versa sharing their electrons with the carbons. If you count these electrons up, each atom now has 8 electrons around them. 4, 5, 6, 7, 8. 4, 5, 6, 7, 8. Thus making them stable in this form. Also, since each single bond is in the sharing of 2 electrons, 1 from both atoms, we can tell that these molecules would look like this is 4 electrons that are being shared between the carbons and a single oxygen. So this would actually mean a double bond right here. So it actually result in this structure, as you can see here. So the next important thing I want to discuss is the difference between an alkane, alkene, and alkyne. An alkane is simply a single bond, and it appears like this. As we've been drawing this thus far, we've drawn it over and over and over again. An alkene, on the other hand, would be a double bond, as seen on the last slide, right here. So it's represented by this equal sign looking thing, 1, 2 bonds. And then, as you can guess, a triple bond would just be 3 of them. And a triple bond would be an alkyne. So, and a single bond is when a sharing of 2 electrons is present, 1 from each atom. So an alkene, or a double bond, would be 2 electrons from each atom is being shared, as seen here. And then alkyne, on the other hand, would be 3 electrons shared from each atom. So 3 from this carbon, 3 from this carbon are being shared in this triple bond right here. And so these are the important takeaways. Just know what an alkane, alkene, and alkynes, and that a single bond results in a sharing of 2 electrons, 1 from each atom. And this is the relative strength, is this SpongeBob meme. So alkanes are the weakest, while alkynes, the triple bonds, are the strongest. So next I want to talk about how to go from skeletal structure back to the molecular formula, which includes the carbons and hydrogens. As said previously, skeletal structure is a simplified form for understanding organic molecules. Molecules at step 1 and step 3 of this are essentially both the same. However, understanding of skeletal structure will be necessary as some molecules on test will need to be simplified, and you can't give the molecular formula. However, this is how to go back if you wish. So the first step would be to number the carbons in the ring and take note of the 3 double bonds of alkenes. Next, following the octet rule, I'll draw in all the hydrogens off the carbons. Since each carbon atom is in a single and double bond, this means that each carbon is sharing 3 electrons, thus can share 1 more. To be most stable, it'll want to share its 4th electron, which will be done with hydrogen. And since this molecule is in the same orientation even when rotated, every carbon atom will have 1 hydrogen present on it, as you can see. So finally, we simply draw and replace the numbered intersections with a C to depict a carbon atom as seen here in step 3. So now all hydrogens and carbons are present in this interpretation of this molecule, and this molecule is benzene. So I'm going to go ahead and go back and number these, and then number these, and I add my hydrogen. And then make sure you don't forget your double bond, because I almost forgot my double bonds here. So put your double bonds. And that would be your answer to your unsimplified form. So now I'm going to go ahead and redraw these molecules as examples. So first take a moment and pause and answer these with what you think. Your job is to redraw these molecules. The first you'll draw to skeletal form, and the second you'll draw back to the not simplified molecular formula. Okay, so the first, I'm going to draw this back into skeletal form, as I've currently been giving the molecular form, not simplified, which, as you can see, contains the carbons and hydrogens. So I'm going to start by numbering my carbons. Next, in step 2, I'm going to redraw the molecule such that every carbon is an intersection of lines. So, and then this will be number 1 because it's next to the nitrogen, as you can see. The next will be number 2. And then the final down here will be 3, the methyl group, as you can see over there in the original. And then add my double bonded oxygen and my other hydroxyl group down here. And then I'm going to add my hydrogens. You can skip this step, but I'm just going all the way through the process. Once you get the hang of it, you can skip this step. Add all these hydrogens. And then don't forget the hydrogens on your nitrogen here. Okay. And then finally, I'm going to redraw this molecule again, numbering the carbons, but this time removing hydrogens from these carbons. So like I said, you don't have to redraw the hydrogens if you don't want to in the second part. So it's worth noting that you need the hydrogens on molecules other than carbon, including the oxygen and nitrogen here, but you don't need to keep them on the carbons. That's what it's implied that you know what the octet rule is and it's being used. Don't forget your hydrogens on the nitrogen. And then that would be your simplified skeletal structure for that. So then the next one is an example of a problem practicing how to translate skeletal formula back to its not simplified molecular formula. So the first step is normal, is to number your carbons. So 3 carbons in this. Next you're going to want to redraw the molecule, but now with all hydrogens present. So this means that the carbon can have 2 hydrogens bonded. Well, okay, so since we know because of the octet rule, this carbon right here in the middle, this carbon is sharing 2 electrons, so 1 to each of its single bonds with the other carbons around it. So this means that the carbon can have 2 hydrogens bonded, so it shares another 2 electrons. Although this would put the carbon at the stable octet. Altogether, this would put the carbon at the stable octet, having 4 atoms bonded to it, sharing 8 electrons. So right here, I'm adding the hydrogens. So that'll mean that those are now at a stable octet, as they're sharing 8 electrons all together. And then I'm going to add the hydrogens here on the nitrogen. And then finally, I'm going to redraw this. Now I'm going to put the carbon atoms in. And redraw everything like normal. And then wherever I see the intersections that I numbered the carbons originally, I'm going to put a C to represent the carbon atom. There's 1, 2, and there's the third. 1, 2, and 3. And then looking back to the original drawing, I'm just going to add my double bonded oxygen and my hydroxyl group. Hydrogens. And that would be how you go back to the unsimplified non-skeletal formula of a molecule, where you can see all the carbons and hydrogens present. So last but not least, I just wanted to discuss the main takeaways of this whole presentation. So the main takeaway was that I want students to understand that main groups elements tend to bond such that each atom has 8 electrons in its valence shell. This is the octet rule. Next, I want students to understand that alkane is a single bond, alkene is a double bond, and alkyne is a triple bond, and the weakest being an alkane with the strongest being an alkyne. And finally I want students to realize that a covalent bond is a sharing of electrons, so 1 electron from each atom. So that's 2 electrons are being shared, 1 from each atom. And the strength of that would just depend on if it's a double, single, or a triple bond. Thanks for watching.